Okay, I think we can start. Andrew, if you want to make the introduction you made.
Okay, sure. So my name is Andrew Owens. I'm a graduate student teaching assistant for Unified Engineering here at MIT. And Professor de Weck, who organized this, was unable to join us today since he's traveling, so I'm handling things on the MIT side of things. And we're really excited to get a chance to do a Google Hangout with the Solar Impulse team to see the aircraft. I'm here with a bunch of sophomore engineering students here at MIT. They've been studying aerospace engineering for the past year. We'll have a little bit more details on this course in the future, but we're excited to get a chance to talk to you guys, hear about the project, and ask a few questions. So thank you for joining us.
That's great. Our pleasure to be with all of you. Good, I guess, good morning for you. Talking to the MIT, it reminds me the good year I spent in Boston. It was in the mid-80s, but I switched to the business part at the Sloan School at the time, so it was not about technology, but still it's a great souvenir for me. So pleasure to have you all with us this morning. Maybe just a few words about the project. I'm sure you know already quite a lot about what we are doing, but maybe just to position well the discussion. What you see behind me is is our second airplane, which we just presented to the media a couple of weeks ago. We hope it's going to be ready for the first flight in about 2 to 3 weeks from now. We just finalize a certain number of software bugs and all the systems that you have to test to make sure that during the first flight everything will be working very fine. But as I mentioned, this is the second airplane. So the first airplane we built, which we flew 3 years ago, was developed just to see if we could fly day and night. And that's what we did in 2010. So this was the first airplane ever built, which theoretically has an unlimited endurance. That's what makes it very special. And in 2 words, why can we do that? Well, first of all, as you know, we collect energy directly on the airplane, so from the sun. But more important, we had to build the most energy efficient airplane. So everything was done to reduce its energy consumption. That's why, in fact, it's so big. We have the wingspan of a 747, or this one is even larger than a 747. But that's the weight of a car. This one slightly above 2 tons, so it's already a nice, of course, a nice car. But still, that's extremely small. That's the wing loading of a hand glider, but with a 70 meters or 240 feet wingspan. So the question, of course, when we built was to see if it could fly and how we could control it. So this was the main question, and we of course developed a simulator for that. And interestingly, when we did the first flight, it was almost impossible to land. We were either on the left side on the runway, on the right side, but never on the center line. So it was quite difficult at the beginning to understand its behavior, and everything was happening so slowly that we always overcorrecting what we were doing. But slowly we started to understand, and that's when we were ready for the first flight. But you also know that we just don't want to fly for the fun of it. And we really want to demonstrate what we can do with these technologies and show the potential in relation to energy savings. And what we have this airplane is slowly finding its way into home building, into other transportation means. And I think we have the unbelievable potential to reduce the energy we consume, certainly by 50% if we would apply extensively these technologies everywhere. So that's the message we try to communicate with this project. That's what we aim for with the flight around the world that we plan next year. So maybe enough talking on my side. I'm sure you have a lot of questions and we'll be able to tackle different points together. I know that you have been working also on different projects. So I'll let you maybe start with the questions.
Before we get started on that, we have a little information on our flight competition that the students just completed. I'm going to see if I can share my screen here. Of course. There we go. So I have a brief slide deck. Okay, so can you see these?
Yes, I can. All fine on my side.
Okay, excellent. So this is just a few slides on what we've been doing here at MIT for a little background. So starting off with some history of the department, we're actually in our 100th year of aeronautics at MIT. The first course was in 1914, and then rapidly after that it grew. We had the Wright brothers wind tunnel built in 1938, and then with the dawn of the space age, we added Astronautics, which is where we are now. Then we have 60s, a lot of work with the Apollo program, the space program, and then a sort of related endeavor was the Daedalus project here at MIT to have a world record in human-powered flight, which flew from Crete to Santorini on the power of a human alone. So right now we're celebrating our... Sorry?
Yes, I remember that. It was a great project.
Yeah. So now we're celebrating our 100-year anniversary, and for many of those years, Unified Engineering, which is this class, has been sort of a flagship course for the sophomore engineering students. And it's focused around the idea of conceive, design, implement, and operate, which is sort of changing the idea of an engineering education away from being purely disciplinary to bringing the disciplines together and looking at the life cycle and systems perspective, which is what has been adopted in the Aeroastro program here. So each student in this class has carried out full life cycle product and system designs at least once, many more than once, and have outcomes-based learning objectives that include soft skills like communications and systems thinking and other things that I'm sure you guys find very important with your project as well. Mm-hmm. The Unified Engineering Flight Competition, which we had just recently, has been a tradition in this class for about 20 years now, and they apply what they've learned over the course of the year to work together a team and build an aircraft, a remote-controlled aircraft. But each competition is a little different, so they can't just copy designs from previous years. So this year, the theme was green aviation. It was inspired by the Solar Impulse project, and so we're very glad you could join us today. And effectively, the mission was a two-part mission where at the beginning they had to complete 5 laps of an indoor course, and then their time, the faster you could do it, the better you performed. Then they had the option to recharge their aircraft batteries under lamps, and the time spent recharging would detract from your score. And then finally, the final phase was an endurance mission to see how many laps you could complete before the batteries run out. So I've got a little bit of video here from the competition and some of the build process. So this is our hangar down in the workshop. Mm-hmm. We've got a lot of teams bringing their aircraft together, putting solar arrays across the tops of the wings. I think we had 65 students participating in the competition this year in 16 teams. So a lot of different aircraft designs. And then the event was public. We had a lot of people from the MIT community show up, and it was a lot of fun. There's Professor de Weck keeping score. One interesting point, you mentioned the wingspan of your aircraft. The wingspan of the aircraft in this competition, I think we had a range from just over 1 foot to 10 feet. So a very diverse design set there. I think there's, yeah. Controllability was sometimes an issue.
Yeah, we had the same, so don't worry, you're not the only one, huh?
So just to give you an idea of what we've been doing here. So now, yes, there was the summary of the competition was that 16 teams competed. We had 5 of them chose to use solar panels. And the winning team, Team Frizzle, which is up there, had 6.75 points, very good score. And then the best solar team was Team Sonic Doom, which is back there. And then tomorrow we'll have the awards ceremony for the Unified Flight Competition. So now we have time for some questions and discussion. Let me get the video back.
That's great. What was finally the learning? I mean, if you look at the teams that won the competition, what was the learning on your side? Was the choice of technologies, the angle from which, in fact, the team started from, or the execution, or sometimes maybe the controllability, simply said. Sometimes the most complex projects have the highest potential, but you can't finalize them. So what has been the learning from your side on this one?
It was probably time management, I know, at least for my team, because as you mentioned, the most complex designs might perform the best, but we didn't have enough time to execute them. My team actually came third, and we decided to optimize our plane for weight and use a design that was generally pretty similar to one that we'd tried before otherwise, because we didn't have time to go through all the possible ideas and come up with a really perfect design. Mm-hmm. And so instead we optimized for weight, and we built something similar to what we built before and cut down the weight and made thinner wings and had a slightly higher aspect ratio, and that turned out to work pretty well for us.
Very good. Congratulations. But we are facing a little bit the same debate, in fact, interestingly, between the first and the second airplane, because the first airplane was simply a prototype, a design to see if this technology works and see if we were going to the right direction, aiming for this flight day and night. So efficiency was really the key word. So everything was linked to efficiency on our side, and I would say not much more. But it was a very simple airplane, and now the airplane that you see here is designed to travel. So we made it quite sophisticated, and of course the main question is, are we too sophisticated? Because the level of complication is exponential. It increases in an exponential way, and the interactions between all the systems also creates quite a lot of potential difficulties, and I'm not sure where we are currently. I'll be able to say more in 6 months from now if we have been too complex in what we wanted as systems on board of the airplane, or we just aren't the target. But that's the question I have currently, and sometimes I have difficulty to sleep because of this issue. You can see simply on the picture we have a retractable. That's an outrigger. We wanted to have some autonomy with the airplane, so we made outriggers. But if you have outriggers, they make drag, and if you have drag, of course, you consume more. So we needed to make them retractable, and so on and so on and so on. So that's a major issue.
Does anyone have any questions?
Yes, hello there. An important part of this flight will obviously be the human part now that you have it built. So I was wondering, would it be possible to see the cockpit a little bit closer and perhaps show how it will be for the pilot to be in there for, I think, the 20 or so days that apparently the flight is supposed to take around the entire world?
Sure, with great pleasure. That's in fact, that's a question we had, and something to solve is how to make the pilot sustainable now that we have an airplane which is sustainable in terms of energy. So there has been, of course, different questions there. Let me climb, and I try not to fall down or to do something stupid here because it's quite high. This airplane is gigantic. You should see them physically. But here you have a look in the cockpit. You can first you can see the instrument panel that we have. It's not on currently because we're working on the airplane, but it's quite sophisticated airplane. What we build is some kind of an autopilot. It's a stabilization system because it doesn't have all the function of an autopilot that you can find on airliners. But what we made differently is also to have something like a virtual copilot. So that's an electronic box which supervises what the airplane is doing, but in a completely independent way. So it has a different data source. It's completely independent from other system, and we can ask, in fact, this virtual copilot to set an alarm when we have a negative trend. Normally, when with autopilots, they just make an alarm if it disconnects. But here we wanted to have an information based on a trend. So, for example, an increasing yaw or an increasing bank angle. And this will help us to get alerted when we rest, because of course when we fly over the ocean, we'll fly up to 5 days, 5 nights, and alone. So we need to rest, and what we plan to do is to have resting period of about 20 minutes, maximum duration. And during these 20 minutes, we can lay down. I mean, you can see here the the backrest of this seat. You can see the space on the back. So this seat can be set fully horizontal so that we can do this 20-minute resting. And then we will be waken up, and then we can control what the airplane is doing, and eventually do a second rest later on. But this is short enough so that we know we don't move too far away, and we are completely away from other traffic. So we would have a separation from other traffic which is large enough so that during these 20 minutes we don't interfere with any other potential traffic to keep it safe. So here I'm setting the cockpit. You can see that's the view laterally. We don't have the protection on it. It's just the structure itself. But you can see, in fact, what we have and what we will be using for this flight. So ergonomy was key, and ways to make this the pilot sustainable over time. So any other question?
Yes, hello. One problem that my team ran into on our flight was figuring out how to best house our electronics and other components in there so that we could both protect them from influence of drag and also minimize the weight there. And we ended up having a lot of problems with weight. I guess my question is, when just aside from the wing, when you're considering just the aerodynamic design of the body itself, of the cockpit, what is your main concern, or I guess what's your process for designing the entire cockpit where you house all of your systems?
I mean, there has been fully based on first on this question of efficiency. You can see now I put myself in a horizontal position, so if I sleep in, ask the team to wake me up now. But that's the way we would rest, simply in this cockpit. Also, weight, of course, is the most important factor. But what we try to understand is the trade-off between efficiency or energy consumption and weight. Because you can make parts more efficient, but very often they are heavier. and of course you have to know what's the best solution. So we try to understand, in fact, this trade-off factor. And what you see in such an airplane is that you have what we call some kind of a multiplying factor. So if you increase the weight of the airplane by 1 kilograms, because you have an equipment which is heavy by 1 kilograms, you need to increase the weight of the airplane by, let's say, 4 or even 5 kilograms. So the multiplying factor is 4 to 5. So each gram is important. So I think weight has been the most important factor, but of course afterwards you have to keep safety in mind. So flying 5 days, 5 nights, we needed an airplane reliable. So we needed some redundancy, which has a negative effect on weight, and that's led us also to make an airplane more aerodynamically efficient. If I can put it this way, the wingspan of this airplane is 8 meters more than the wingspan of the first airplane. So I don't know if I answer your questions, but at least that's the thinking which was behind this this process.
Oh no, that was very helpful. Thank you very much.
So another question?
Hello. I was just wondering if you have any more information that could give us a better idea about the cruise conditions for the plane. So what altitude will you be flying at, and what will be your airspeed, etc. Just trying to get an idea of what's the most optimal conditions for the plane you're designing.
The goal was to have an airplane which has the smallest sink rate, because that's with the energy you use in the electric motors, you will compensate in fact this negative sink, and so the airplane had to have a low speed, very low cruising speed, quite a thick profile, and a profile which was efficient at really at low indicated speed. So the best speed we have is 24-25 knots indicated. It gives us a sink, but I talk about centimeters per second here. That's something like 26, 27 centimeters per second. So I know that you have more feet per minute. You should make the calculation, but it's almost half of what you get on the best gliders. Because the best gliders, they go on more L over D, and the sink is not what is the driving factor for their design, but compared to such an airplane, it's almost half, and that's basically how we could reduce the amount of energy we need to fly horizontal. And then altitude is a way to store energy. So we climb every day to 28,000 feet. It's just below the altitude of the airliners. So when we cross the ocean, for example, they are all above flight level 300, so we don't interfere, which is great. And we are at minus 40 degrees outside temperatures, minus 40 degrees centigrade, which is also good because electronics normally are tested up to this temperature. If you go below this temperature, minus 55, you need military specs, makes it much too complex and difficult. So that was another reason why we didn't go higher. So altitude is a way to store. So every day we climb to Mount Everest because that's about the altitude of the Himalayas chain. And every day we'll go down to 5, 6, 7,000 feet, so quite low. So that's a burden for the body. Oxygen is a burden also because it's, of course, it's not the natural environment. So this makes it more difficult with temperatures also varying from plus 25, 30 degrees at daytime to minus in the cockpit to minus 20 at sunset. So we had to do it because I think that was important to be able to do this flight through the night. But of course, as I said, that's a challenge for the pilot as well.
Firstly, by about what kind of factor did you manage to reduce the weight of the plane just by, for example, having a non-pressurized cockpit and just affecting the basic human factors? And how did you deal with problems of dead weight, for example, weight that's only required for takeoff and landing, like the landing gears?
Well, the reduction in weight, in fact, is a complex question because a pressurized cabin, I think, could be done quite simply and in a lightweight, with a lightweight strategy. But what we also wanted was a safe exit in case of big difficulties. And if you need to have a big exit doors, which is pressurized, that's what makes it difficult. So that's the reasons why we said, okay, this is too difficult. It's a project by itself. We're not going to do it. We have too many new technologies to look at. So let's really focus on what is key, and this burden we'll be able to take as a pilot. And your second question was?
Weight, for example, that is only required during landing. That's not actually been, in any way beneficial to crews, like the landing gear. How did you deal with that?
Well, it's not much. I can show you the way we design it. The outriggers that you have seen can be taken away. I mean, when we cross the oceans, I think we'll take this away to reduce the weight of the airplane. But if I take the main landing gear, that's in fact this part here. So we have one single one main landing gear, which takes all the weight at landing, and this is about 25 kilograms, including the wheel. So it looks complex, but it's mostly in carbon fibers, with the exceptions of the part which keeps the wheel, which is in some kind of aluminium, but that's not much more there. And the other wheel is on the tail, but it's extremely small, so this is very light. And as I said, the outriggers can be taken away, so dead weight is really minimized in this airplane. Now you can see the tail wheel here is almost nothing. So in fact, the weight is the result of the work of every component. The tire, for example, is a special design made by Michelin. So every part has been optimized. In fact, to try to reduce the weight. So the small tire here, for example, and that's, I think we saved a couple of kilograms on this part as well here. So everything was done, in fact, to make sure that we reduce the weight everywhere, and it's only the sum of all these which led to what we have achieved here. We have, I mean, just for you to imagine, the thinnest layers we have for carbon fibers that we use for the main spar of the wing weighs, one layer of carbon fibers weighs 25 grams per square meter, which is a third. I mean, you certainly use other ways to measure the weight, but 25 grams per square meter is a third of the weight of the paper you get from the printer that you have when using a computer and printing. So it's unbelievably light now. So these are technologies we developed between the first and the second airplane to get this weight reduction.
All right, thanks a lot.
So I think we're almost out of time. Do we have time for maybe one more question?
So we have a last question, or?
All right.
So with our aircrafts, we're like really fortunate to be able to like crash them and rebuild because balsa wood and foam are relatively simple building materials. But your wingspans are like 70 meters, and you have like 12,000 solar panels on each wing. So how does that affect your ability to test and prototype for these planes?
How does, I didn't understand the last part of your question. How does it affect what?
I guess just the complexity of your structure, how does that affect your ability to create prototypes and do testing for your aircraft?
Oh, it's of course it's a tremendous increase in complexity. One difficulty we had was to integrate solar cells, which makes the upper surface of the wing. The solar cells, maybe I can just climb over there. The solar cells are not glued on the surface; they are the upper surface of the wing. And the question was how to integrate them on the structure so that you keep a perfect shape, but you disconnect them in some ways from the structure when it bends and when you have torsion, so that you don't damage the cells, which are pretty fragile. So that was a very long study we made to be able to reach this quality of surface. Maybe it's difficult to see it, but the surface of the wing is of unbelievable quality. But also, in fact, we had to integrate them on the ribs in such a way that they are, in some ways, as I said, disconnected from the structure so they don't break when we fly in turbulence. So these are the questions that we had to solve to make it feasible. I think we can.
By any chance
Yes?
hiring? Are you by any chance hiring?
Excuse me, I'm sorry, I didn't get you with the laughs on the back there. Can you repeat?
Are you hiring by any chance?
We are. I mean, we always have some opening for trainees. Minimum time is 6 months because below 6 months doesn't make any sense to come and work with us. But yes, we do. We have openings also for the mission for next year, so integrated into the mission control center. We don't know where it's going to be located yet, but somewhere around the world at a fixed location, of course. But yes, we have had many students. We have also retired engineers who are extremely experienced, and the mixture of both was great. I mean, to mix new ideas with experienced people was tremendous. So yes, I mean there are openings, and if you want, you can send your resume.
Thank you.
So I think we get close to the end of the Hangouts, as I hear. Is it correct? Yes.
Yes.
Unfortunately, it goes too fast. Also on my side, it was a really great pleasure talking to you, and would have loved to see you models, but it was already nice to discover them on the video. So congratulations to you, and let's keep in touch.
Absolutely. Thank you very much for joining us.
And my best to Olivier also when he's back from his trip.